All right, so what we're going to be doing here is developing the very commonly used five kinematic equations that sort of allow you to equate the aspects of motion when an object has uniform acceleration, right? Aspects of motion being final velocities, initial velocities, change in position, and time, and then the acceleration as well. Note that these work for situations where you have a uniform acceleration or constant acceleration. If your acceleration varies or changes, then either you have to use calculus or, well, you could use these equations in an average acceleration situation as well. But for most high school physics classes, you're going to be dealing with either you'll just kind of make the assumption that it's an average acceleration or a uniform acceleration. So, in that fact that let's say I've got where do these equations end up coming from? Let's say I've got a object and its velocity increases from some initial velocity to some final velocity, okay? And I'll write it like this, okay? And during that time, it had some sort of initial time, and it had some sort of final time, okay? And that's an F right there. It doesn't look like an F, but it should be. Okay, let's try that again. Okay. Now, because my velocity is changing, I can assume that it has an acceleration. And because this is a straight line, it is appearing to be a uniform constant acceleration. And if I effectively just take the slope of this line, okay, then which is going to be this point is going to be the y coordinates are velocity final and the x coordinates are time final. This point, the velocity is initial and time initial. If I take the slope of this, it's final velocity minus initial velocity, or change in y, which is this distance, or the change in velocity, over the change in time. And so I'm going to go with velocity final minus velocity initial over time final minus time initial. And so these are vectors, okay, because we can end up designating a vector on here, for example, like west or north or something like that, right? So we'll just leave it generic for now. And that's basically what we're looking at, right? So, and if you look closely at this, the units in the top are meters per second, and then the units in the bottom are seconds, we'll just kind of say. And so if I've got meters per second divided by seconds, that's meters per second squared, which, as we know, is an acceleration, okay? And so if you kind of look closely at this, you'll see in many textbooks that it's final velocity minus initial velocity over, and then for whatever reason, they unite the time but not the velocities, and it ends up being acceleration is equal to the change in velocity over the change in time. And this is oftentimes referred to as the first kinematic equation, okay? Now, I know I said that there were five of them, okay? Well, again, let's take a situation where I've got a final velocity and an initial velocity, and I've got a time initial and a time final. And I want to, instead of taking the slope like I did back here, the slope gives us the acceleration, okay, according to the units that I'm using. If I instead take the area under the curve here, you will actually get the displacement, all right, or the change in position, the change in position. And basically, and we'll see this when we look at the unit analysis on our final equation here. Basically, if I look closely at this shape, I've got two parallel sides of a quadrilateral with one set of parallel sides is known as a trapezoid. And so if I try and figure out the area of this trapezoid, it's base 1 plus base 2 divided by 2. Then you multiply it by the height. So just a reminder, the area of a trapezoid is base 1 plus base 2 over 2 times the height, okay? Now, if I go ahead and assign, according to this graph, base 1 is basically just this distance, which is delineated as the initial velocity of the object. Base 2 is this distance, which could be considered this length, the length of this dotted line, which I can use the y-axis to measure that length, and it's known as final velocity of the object. So base 1 and base 2 is actually just the sum of the initial and final velocities. Oops, excuse me. And so, therefore, I've got velocity 1 plus velocity 2, these are again vectors, over 2 times the height. The height of a trapezoid is the distance between its two parallel sides, or the set of two parallel sides. If you look closely at this, the distance between these two lines here is going to be delineated with a x value or a time. And so this distance is actually just a delta t. So it's a change in time. And what is this going to give us? This is going to give us the area, which is a change in position. So I can see that my displacement, or change in position, is equal to the sum of the initial velocities and final velocities. I wrote velocity 1 and velocity 2. Sometimes it's velocity 1 and 2. I'm going to stick with final and initials. So this is initial and final. The sum, half of the sum of those times time. And actually, if you look closely at this, this is also known as the average velocity. And look, if I do average velocity and I divide this time over here, average velocity is equal to change in position over time. So this actually equation makes sense on several levels, okay? And again, if I look at the units here, the sum of two velocities is a velocity. A velocity divided by a scalar 2 is just going to be a velocity. And a velocity times a time gives me a distance measurement unit. And so it's a change in position, okay? So I end up with that. So these are my two initial sort of what are known as the sort of first two kinematic equations, in my opinion. And now, if you take these two equations and you do some algebraic sort of magic on them, you're going to end up getting a series of other equations, okay? And they're listed down here in this chart. And I'll just do one of them, and I think that the rest you can kind of maybe do. So for example, look, here's the first one, right? Here is here's the other one that I have. Well, it's written a bit differently. The change in position is half of the sum of the velocities times time. I tend to write it like this, but we can also write it like this, okay? So anyway, how do we end up getting all of these other ones here? So this one we know, this is just the concept of the slope of a velocity time graph gives us an acceleration. And this one is the concept of the area under a curve of a velocity time graph gives us displacement. So those two concepts are valid. Now, how do we get these other three? Well, it's just a simple matter of taking something like this and plugging it into this one. So I'll start with my two initial equations here. Acceleration is this guy. This little pen is broken here. I'm going to get rid of it, delete that guy. Okay. So I'm going to say that my acceleration is equal to my initial velocity, my final velocity minus my initial velocity over time. Okay. And what I'm going to do here is I'm going to take this one as well, and I'm going to solve for time in both of these. And then I'm going to set the two equations equal to each other. So if I solve for time in this one, and I solve for time in this one, then I get the following. So I guess I'll just go ahead and do this now. Solving for time in this equation allows me to put time here and acceleration there due to sort of the idea of cross multiplication. Then if I take this equation here and I solve for time, I'm basically just I got a half. So the half is multiplied by time. So it's basically multiplied by 2. I have to divide half over. Remember, dividing by a half is the same as multiplying by 2. So when I divide this half over, I can effectively just take the displacement and multiply it by 2. And now I also have the sum of the two velocities here. And I'm going to divide that over. Okay, so I'll divide that over. So that's the sum of initial velocity plus final velocity. Okay, and I'll set that equal to time as well. Well, now focusing on these two equations here, if I basically just say, hey, look, right, I'll zoom in a little bit. If I focus on these two equations here, basically, if I'm talking about the same object that has some final velocity and some initial velocity, and it has some change in position, and it has some acceleration, then these are the times. So these times will be always the same. These two equations describe the same object. So therefore, this side and this side could be set equal together because they're both equal to the same value at all cases. So effectively, I'm just left with final velocity minus initial velocity over acceleration is equal to 2 times change in position over final velocity plus initial velocity, okay? And now I'm going to drop my vector symbols here because the reason why I'm doing that is because I'm now about to multiply some vectors here. And we don't have at this level of physics a technique for vector multiplication. We do have vector addition and subtraction. And so I'm going to do this with the scalar versions rather than the vector versions. And we'll get around the fact that these are scalars when we apply the formula in the context of the situation. We'll be able to determine the final direction of the acceleration or the change in position or different things, okay? So I am just getting rid of the vectors, but be careful. That's because we don't really have a vector multiplication equivalent right now. So if I cross multiply here, I get this times this, which is VF minus VI times VF plus VI. Interesting. Is equal to 2 times delta D acceleration. Now, these two guys are, if you look closely, the difference of squares already solved. So this actually just turns out to be final velocity squared minus initial velocity squared. And that's equal to 2 delta D A. Okay? And if I add this initial velocity over, I end up with final velocity squared is equal to initial velocity squared plus 2 delta dA. And you would find this as your third kinematic equation. And it's going to be over here on this thing over here. Where is it? Oh, there it is. This one. There it is. And then if you effectively just do that with the other situation, so rather than solving for time, you solve for final velocity in both of these yellow formulas, then you would be able to find another of the kinematic equations. It's going to be the one on this list. And then again, instead of solving for final velocity or time, you go up here and you solve for initial velocity and you set them equal. You'll be able to find this one over here, okay? So these are the origins of the, we call these things, the 5 kinematic equations. And then we'll spend quite a bit of time in pretty much any physics class and apply these in both two dimensions and, one dimension and 2 dimensions. We won't be really applying them in 3 dimensions, though you can. Though if you were to apply these in 3 dimensions, it would be much more appropriate to use a different type of vector rather than a geometric vector. You'd want to use a Cartesian vector. So we can talk about that in calculus class or a class dedicated to vectors. Anyway, so that was the developing of, only 3 of the 5 kinematic equations, but that's kind of the idea. In some next videos, I'll take many of these equations and start to apply them into 1 and 2 dimensional situations, and we'll solve for those.